Accelerators are used in a large number of areas and for applications now, but what we're interested in is moving that whole story forward with the fact that the technology of accelerators is advancing rapidly, and that Fermilab is kind of pushing the envelope on that. And then, as you heard together with Argon, we think that we're really dealing with new technology now that can be applied to almost situations that we haven't really thought about. So we're going to sort of probe into that area. So today, some of our goals will be to announce the launch of the DOE Accelerator Stewardship Test Facility Pilot Program. Okay, long name, to promote lab, industry, and university partnerships on accelerators and related technologies. So this is a new direction for the government. It's not something that existed, should say federal government, new direction for the federal government, in that they believe there is an opportunity here, and this has been growing over the last several years. So this is not a new thought, but it's a new initiative, and it's finally getting some funding. It has rather strong support in the Senate, so we see this as a program that's going to grow in the future. We want to inform you about laboratory technical capabilities, understand your biggest challenges and whether a partnership might be useful to address them, and discuss possible partnerships with some of you we know and some of you we don't know. Part of a larger effort to encourage national labs to partner with industry to promote innovation in U.S. industrial competitiveness, launch new industries, and create jobs. So that's the thrust of this program, and how that plays out will depend on how we do, I think, in discussing where we want to go. These approaches have been used elsewhere successfully, example Germany, and they've been recommended by a number of, I'll call them fancy committees. Blue ribbon panel's a nice way to say that, but a lot of people think this has great potential. Okay, so here's a nice picture of Fermilab. You can see we one time had the world's highest energy accelerator, the Tevatron, which has now passed the baton on to Europe, to CERN as the highest energy machine. But we are now producing the most powerful neutrino beams in the world here, so we've been moving in the direction of high intensity rather than high energy. And so that, I think, has the greater application potential to the private sector than just going to higher energy all the time. So that's basically the strategy. So to carry out that mission, Fermilab designs, builds, and operates high energy, high power, high reliability accelerators. And I would say in combination with Argon, we address quite a broad range of accelerators. We address different technologies, different capabilities, but in the end, I think we cover soup to nuts in almost everything that goes on with accelerators. All right, so at Fermilab, we built state-of-the-art accelerators to understand our world via particle physics. I'm not going to spend a lot of time discussing quarks and leptons to you. I'm sure you've already read up on that. So, but there have been many, many discoveries over the last 40, 50 years related to understanding basic nature using accelerators. And I think that's the message. We use them as tools of research, but they can be used for other purposes. So that's all the particles that were discovered with accelerators. And in particular, if you go to this, we call these families, first family, second family, third family. Fermilab discovered the top quark, the bottom quark, and was the first to observe the tau neutrino. So 3 of the 4 in the last family were discovered here. So that's pretty amazing. Compliment to my colleagues from the past. Despite their impact on science, most accelerators that have been built are used for other purposes. So there's about 30,000 accelerators in use around the world. Sales, big number here. Accelerators touch a huge number of products in terms of their revenues or sales, and they're a major impact on our economy and in our health, day-to-day health, and well-being. So some of the products you see here are I'll go into a little bit of detail, but not too much. Hardening of tires, electronics, wrappings of various kinds, electron beam welding, and so on in the aircraft industry. So lots of applications that you probably haven't thought about. Okay, so accelerators are essential tools in industry. So ions are implanted into various metals to harden tools, reduce friction for materials for implants. They're used to harden surfaces, modify optics, improve the quality of various gems. They're used in solvent-free printing, which is environmentally friendly and the direction I think lots of people think we should be going. Food irradiation, I'm sure you're familiar with, and medical accelerators. Okay, so a wide range of industrial applications make use of low energy beams of electrons. So electrons are used to drive chemistry. These are low energy numbers for a place like Fermilab. We barely understand this lowness, but that's okay. But the megawatts is the challenge. So when you think about power, it's going to be the energy times the current. And so we're talking about high current accelerators. So electron beam irradiation improves heat resistance of coatings, wires, cables, cross-linking polymers. So what you're seeing here is the electron is used to break the bond so that you basically form a new structure in the polymer so that you have a harder material, and that's what's used with radial tires. You can see there's 1,500 dedicated facilities around the world doing things like that. Okay, on this slide we're showing the impact of electron beam welding and machining, and you know, it's used in all kinds of things in your car, for example, in jet engines, in turbochargers. You can see roughly the size of a electron beam welding machine here in that picture by Pavik, made by Pavik Industries. Accelerators are used for national security. So here you've determined that there's an old car sitting inside of this container, so that must be interesting to the government. More than 2 billion tons of cargo pass through U.S. ports and waterways annually, and accelerators are used for cargo scanning and active interrogation to detect special materials. And we've talked about using other particles than just X-rays, so there's actually potential for doing more interesting things, I would say. Accelerators in medicine, I'm sure you're all familiar with proton cancer therapy, where you're using protons rather than X-rays. The seminal paper on this subject comes from Bob Wilson, who was the first director of Fermilab, who pointed this out as a possibility. And the first, I would say, facility-located machine was designed and built at Fermilab, and it's been operating at Loma Linda in California for decades now, working well. There's a worldwide industry in this now, and it's obviously had a big impact. So there's other technologies. People are looking at smaller technologies using superconducting technology to make things more compact. And this is still very much a growing field. Okay, so that's what exists. Now, future accelerator applications are envisioned. So we give you a significant number of ideas that I would say that we've been thinking about. So there's the energy and the environment associated roles that you can use accelerators in, more industrial, medical, safeguards, and security. And I'm going to go through just a few of these for you. So, but one of the principal ones is the fact that accelerators can drive chemistry. So you're going to use the electrons from the accelerator to adjust the bonding of various molecules. The way it's done traditionally is that you heat things up, and it's a very inefficient process. And so you have to heat up the material or the gas or whatever to give enough energy to the system so that the bonds break, the electrons are ionized, and a chemical reaction can take place. Or you can use an electron beam to actually knock the electrons off, which is much more efficient. So that's the basic idea, is that you have a high enough energy electron to ionize the atom or the molecule that you're interested in modifying. So accelerators can be used for the environment. So here's an example with water. So they're effective for destroying pesticides, organics, pharmaceuticals, You can use them for sterilizing municipal water, for example, or sludges. It allows water to be reused, and of course water is becoming a super valuable resource. It's the oil of the future in some sense, so I see this as a potential significant growth industry. Beyond energy, the availability of clean water is the next crisis, and I think most of the planets figure that out already. Technology demonstrations are available, but they're not really deployed, and the question is why? Well, it's just the way we organize ourselves within municipalities. So a small township, say, would have to go out on a limb to put in such a sophisticated facility. So you need some kind of assurance that this is going to work. They're not going to be by themselves. So we think there's ways of working with multiple municipalities that this could be something that becomes quite practical. It should be reliable, could be compact, efficient, high power. So we're showing you in the upper right-hand corner the technology that Fermilab is putting a lot of effort into, as well as argon, and that's called superconducting RF. So it's superconducting materials. This is solid niobium that runs at cryogenic temperatures. And we think you can make compact systems using this technology that would be quite practical. Accelerators can be used for other things. So here you're seeing a picture of the night satellite picture of the U.S. at night, and most of these bright spots are towns or cities. But this is actually the gas in North Dakota being burnt off. So we just waste it, basically. So many wells produce both oil and natural gas, but not all the gas is recoverable. The locations are very remote, so the pipelines are not very economical. They produce a burst of gas for only a few years, so that's why it's flared off. And as you know, methane is not good for the environment. So the worldwide business here, if you like, is 30 billion a year of gas is flared, so it's almost unbelievable. It's equal to 25% of all natural gas usage in the U.S., and it's doing no useful work for us, and of course it's bad for the environment. There are techniques to deal with this, but these are very big, complex, difficult systems to put in remote areas, and so this hasn't clearly caught the attention of industry, and so has not really caught on to be used. However, we think mobile accelerators could in principle be used to efficiently convert the gas to a liquid. So that's the basic idea. You would have a portable system that would, say, be on a tractor-trailer arrangement like I show you here. So the trailer-mounted high-power electron accelerator. So I'm going back to the technology we're developing now. It's kind of state-of-the-art technology. The natural gas can provide the local power, and then liquid hydrocarbons can be created and can be mixed and collected with crude oil produced by the well. So there is a strategy to do this. I think it needs to be developed further, but has significant potential. And you can see the amount a single well flares in 1 to 2 years. So it's on the surface of it, it looks like it's a plausible business model you could put together. Coal, of course, is still a major source of electrical power in the world, sadly, I think. China and India are ramping up use of that. The U.S. EPA regulations will reduce coal, but it will remain an important energy source regardless. And so removing and cleaning emissions from burning oil is essential, removing the NOx and SOx, and there's techniques using electron accelerators, again, to be able to do that. And these techniques tend to use far less water than the traditional electrostatic separators. So these are other things we've been looking at. Accelerators for the environment, still highway life extension. So there's a lot of miles of paved roads in the U.S. Most of those are from asphalt. The average road, especially in Illinois, undergoes lots of repairs and repaving every few years. and the U.S. places 550 million tons of hot mix asphalt each year at a cost of about $25 billion a year. So it's a huge industry. And the heavy machinery used to rebuild the highways it has a big carbon footprint as well. So even a technique that gives you a 1-year extension of life of the road would save enormous amounts of diesel fuel and taxpayer dollars each year. So you can think of this as, in an analogy to the way we've talked about radial tires. You irradiate the tire, the molecular structure changes, and the asphalt becomes harder. And that's the logic. Now, it's not as trivial as that. You need additives to do this, but I think this is clearly, it's something you can imagine has great potential. Again, it relies on the idea that you would need a mobile system, and we've gone through sort of a paper exercise here of how much you need, how fast you can drive, all those kind of things, how much value it brings, and so we've started doing some real tests in this area to see how hard we can make it. So that's something we're just starting with. Accelerator technology can be applied to wind turbines, so there are new materials like magnesium diboride, which we refer to as high temperature superconductors. So these are materials that become superconducting at higher temperatures, which are easier to work with. There's been advances in these materials recently that allow them to have very high current densities, which then allow you to have high magnetic fields. And therefore, you can think about absolutely different approaches to wind turbines. And for me, the key thing is they don't have gearboxes. And so they're lighter systems, they're more efficient, and make a fair amount of sense. So I think there's another area we can get into a discussion about. So what's the obstacle? So I think the main thing is the risk and the high cost of entry. You need a lot of experts. You need a lot of understanding of these, I would call them advanced technologies. And so what we've started to do here, which is really a first for Fermilab. So Fermilab goes back to 1968. But I would say this is the first time that we've had a real desire to impact the private sector in what we do. It's the first time the Office of Science within DOE has had a similar attitude. So the idea of technology being transferred in a serious way has got momentum now, I would say. So we have built a new facility which we refer to as IARC. So it's the Illinois Accelerator Research Center. It was a joint project between the Department of Energy and the state of Illinois. And it's to enable Fermilab to work more closely with industry and university partners to develop new accelerator technology, demonstrate new applications, and support accelerator education, to develop new accelerator technology-based products in high-tech industries in the U.S. And IARC is intended to be a portal for industry into the larger core capabilities and infrastructure at the laboratory. So the vision is well aligned with the goals of the DOE Accelerator Stewardship Test Facility Pilot Program, which you're going to hear about from Eric Holden. So as you drove in, you perhaps saw the building. It's a very nice looking space age type building. We have a mission. We want to partner with industry to exploit technology developed in the pursuit of science. So for us to do world-leading science, we have to be at the cutting edge of the technology. That's the simple answer to why we push technology so hard, is to do our science. But we think that is going to have applications, especially in these portable, high-power electron accelerators. That's really what we're focused on. So in summary, Fermilab is actively engaged in accelerator R&D in support of its basic mission, its science mission. Technology we develop, we believe, has applications along, beyond HEP. That's already true. Opportunities for lab industry university partnerships with transformative impacts in manufacturing, energy, and the environment. I gave you a few examples. There's opportunities to create new products and new industries. And the DOE is starting this new stewardship program, which we want to pay attention to and be involved in. And then there's other funding sources within the government that allows us to move these partnerships forward. So Argonne and Fermilab look forward to showing you our capabilities. You'll physically see them today and discussing possibilities for future partnerships. Thank you.